Actually, this first one starts from, I did, when we're talking about the kinetic theory and gases. This is a time when you have to pay attention because you are going to, some of those green questions over there, they are from the stuff I'm covering right now. As a matter of fact, most of them, if not all of them, are from this. And they will be on the test as well. I'm just not reteaching it except for in this one day of review. All right, the kinetic theory. Let me explain what that basically means. If you notice what I use this a bunch of times. Remember this? This little animation. I turn it light. I don't know if it's better with the light on or off. Yeah, it's a little better with the light off. For just a video, I'm saying. If you look at this animation, it pretty much is describing what we feel is the molecular kinetic theory. All right, and a lot of AP now, I've been noticing this for the last couple of years. I've been looking at this stuff. It's model-oriented, okay? That doesn't mean Kate Upton's coming to see you on the AP exam. It means it likes to draw little models, little molecules, and ask you questions about it, like about polarity and intermolecular forces, and should this be a solid, a liquid, or a gas, all kinds of stuff in model format. So this is a great model. This actually is a great animation. It's showing what a compound would look like, or elements, different compounds, different elements would look like in a gaseous phase. Notice the molecules are moving randomly, and they have a lot of energy. Now, if I take away, I have two different kinds, if you can't see that in there. There's blue ones, which are heavier ones, and would have stronger intermolecular forces, be held together tighter. And there are red ones, all right, that are flying around a little bit faster, have a little bit more, you might notice that, have a little bit more energy, it seems like, or moving faster anyway. All right, as I cool this guy down, you'll notice what will happen. The molecules are moving slower and slower. The larger molecules are starting to condense into a liquid phase. The lighter ones, the ones that don't have as strong forces, they're still kind of turning, it's still a gas. But these other ones are, as we slow them down more and more, are getting, you know, basically slowing down, getting closer together, having less energy, and eventually they'll turn into a liquid. Okay? Remember, this chapter is on energy. That's why I'm going over this. The energy of molecules. How do I change their energy? When you heat something up, what you're doing is making them move faster. Okay? Now they're probably pretty much a liquid phase. Every now and then you notice a guy will get enough energy and kind of fly off and evaporate. That's what water does. If I leave a glass of water on the counter, it's going to eventually evaporate over the course of a couple of days maybe, but it will. Every now and then a molecule gets enough energy and flies off. Okay? So if you think of energy in the chemistry term, we always have to think at the molecular level, not at like in physics. In physics, like I said, I can push against this board all day long. Schrader says I did no work because I didn't move a force through a distance. But in fact, I got hot, this got hot. There was a lot of energy. A lot of molecules were moving faster. I just didn't physically move this board. Okay? He always has a cart, and he's measuring how far something moves and what its mass is. Okay? All right, so that's the first little concept from the molecular theory. Put that light back on for me now. And let's get to some of the notes. Now, you're going to follow along with me. They're already filled in for you. You got these notes for real back in the day. I need to go over them because you're going to have several of the questions that are going to come from this topic. Okay? Sticking with that kinetic theory, what holds those molecules together and makes them eventually turn in from a gas to a liquid to a solid. And I couldn't, using that animation, turn it into a solid. But if it was a solid, they would just be vibrating about a fixed position. Okay, they wouldn't actually be moving around and sliding around in different places. All right, well, I want to talk about those intermolecular forces because they are key to determining the phase of something and how much energy they have and how hard it's going to be to pull them apart. So you may remember, I hope you remember these terms. You may not remember them perfectly, but I hope you remember these terms from Chem 1. And if you don't, that's why I'm giving it to you. That's why I'm also giving you this, because it's part of thermodynamics that we understand that the intermolecular forces are what's holding something together. And we're going to do some calculations of phase changes in particular in thermodynamics that we have to understand what's holding these guys together. When I'm talking about intermolecular forces, I am talking about, all these are there anyway. I'm talking about, where'd my picture go? Oh, well, I guess I want to go back one. I want to make a picture. I'm not talking about what holds, for example, water is a classic example. I'm not talking about what holds the O to the H. And we know he has that shape. We've already gone through that, why he has that shape. So I'm not talking about that. I'm talking about if I have a neighboring water molecule. Is there an attractive force between the molecules? That's what intermolecular or van der Waals forces are. Okay? And there is an attraction. It determines, in part, the phase of the substance. If the stronger the attraction, you would expect would be a solid, the strongest ones, then liquid, and then gas. Okay? And that makes sense. The higher the boiling point, the stronger the attraction. Okay? Makes sense. All right, so all that's well and good. Let's talk about the three different kinds. There are dipole-dipole attractions. Remember those from the day, back in the day? Dipole-dipole attractions occur only between polar molecules. By the way, you're flipping along with me here. As we get next page, you go to the next page, okay? Only polar molecules show this guy, and it's the attraction between oppositely charged portions. So take a look. I'm not talking about what holds the H to the Cl. That bond happens to be a polar covalent bond. I'm talking about this. The attraction between this chlorine and this hydrogen. Why would that have an attraction? Very simply. You remember drawing these kind of arrows? We have a partial positive charge here and a partial negative charge there. Remember that? Because he's more electronegative. Chlorine's more electronegative than hydrogen. He's going to pull those electrons. They're going to spend more time around his nucleus. So this guy's going to be a little bit negative. Well, vice versa. This guy's going to be a little bit positive, right? So that positive and that negative are going to attract each other. That's the dipole-dipole attraction. And that's a relatively strong charge, but it's not attraction. But it's nowhere near as strong as a special case of this, which would be what? What would be a special case of this kind of guy? Where it's really strong, the strongest of the intermolecular forces. Turn your page and you'll see. Hydrogen bonds. Hydrogen bonds are really important. You kind of have to mention them somewhere in biology. If you're taking the AP Bio test, you're going to probably have to talk about them somewhere on the AP Chem test. If you're talking about intermolecular forces in any way or water in any way, pretty much. What is hydrogen bonding? Well, it's a special case of the dipole-dipole attraction. What you have here, the very strongest of the intermolecular forces, only occurs when you have hydrogen bound to these three other guys, because they happen to be very electronegative elements. Okay, and so what happens is hydrogen atom, which only has one electron, is pulled. That electron spending most of its time around fluorine, oxygen, or nitrogen. It leaves almost a bare proton behind, almost, resulting in a very strong positive charge, which is then going to be attracted to the neighboring atoms, fluorine, oxygen, or nitrogen's electron cloud. Okay? This gives water its unique properties. Water should not be. You may remember doing this lab. We did a lab where we graphed the hydrogen compounds of a bunch of different elements, 4 different graphs. And what we found was every one of these guys, fluorine, oxygen, and nitrogen, had a ridiculously high boiling point and melting point when you graphed that. It did not fit. It was way high, and water in particular is extremely high boiling point and melting point. All right. It also some of the other properties of water. It is cohesion, the fact that the molecules stick together. The meniscus, you know how it climbs up the capillary tube. Okay, capillary action. Plants need it for that reason too. Water is the reason hydrogen bonds are the reason water has such weird properties. Remember the video we saw on water, the fountains of the Bellagio, and all the other stuff about water. Why does ice float? Everybody, I asked that in their class. Somebody said right off the bat, "Oh, that's easy. I know that because ice is less dense than water." That's going to get you no points if they ask you why ice floats. If that's all you say. But that's correct. There's nothing wrong with that. But it's not descriptive. It doesn't really tell me why the ice floats. The ice floats because as this bond forms, the hydrogen bond forms, when at 4 degrees Celsius, by the way, and this is one of the questions you're going to get on the test too. 4 degrees Celsius is the maximum density you're going to get for water. After that, it starts to expand. I know it's not easy to see this probably on the video or even where you are. Turn that light off again, maybe you can see it a little better. But what happens is, normally, in a normal case scenario, let's take a look. A water molecule hanging out, and they're moving around, and they've got enough energy. They can kind of get in amongst themselves, you know, and they can get real close together and kind of fit together. So they're relatively dense. But as they slow down, and they get slow enough that the oxygen and hydrogen starts to form, the hydrogen bond forms between them into a crystal. That crystal lattice has a lot of space in it, like this here. See all the space. As that starts to form, you actually get an expanding of the less dense expanding of the structure, and that's why ice floats. That's really important to all of life, right? As you learned from that video when I showed it to you last year, and we talked about it too. If it wasn't for that, what would happen? Water would form, ice would form on the top and sink to the bottom if it was more dense. It's not. It actually serves as a layer of insulation on top of a pond, all right, so the fish don't die every winter. Okay, so that's the hydrogen bond. We have dipole-dipole hydrogen bonding, and then we have one that actually is very important in organic chemistry, the London dispersion forces. You can put that light back on. Now, by the way, a lot of these have different terms. Van der Waals forces, intermolecular attractions. I've been noticing when I looked up, I'm always looking for you guys. I have several for this chapter. When we get to the end of the test, towards the test, I'm going to give you some AP practice exams. Okay? Some of them are right out of the previous practice exams, like 2013, 2014, whatever year. They put them out online, and you can see them, and you can do them. You can do those same questions. Okay? But if you go back to 2009, 2003, they're all online too. And you'll find that they use different terminology for some reason. Sometimes they call them dispersion forces. I think they do that now. In the old days, they called them London dispersion forces. And some just use van der Waals forces to be a generic catch-all. All right. I did not give you a very good definition of dispersion forces back in Chem 1. I'm going to do better right now. First of all, it is the weakest. And I told you it becomes important in organic chemistry. Remember when we talked about alkanes? Say like CH4, C2H6, C3H8, and so on. What happens to the boiling points? This is something you had to know for the last test. What happens to the boiling points as I get heavier and heavier, bigger and bigger atoms or compounds? Boiling point rises. I know this guy's a gas with a very low boiling point. I know propane. This is propane. He's also a gas, but you saw this. Was it Lexi that helped me light the bubble? I told you in the old days, I used to light that propane bubble and catch it on fire. I had to stand on the desk because the propane sank. But this one, what did it do? I made the bubble and it rose to the ceiling. Okay? Then you get down to butane. What about butane? Butane lighters, you can see the liquid. It doesn't take much pressure to keep it under a liquid. Octane, it's a gas. I'm sorry, octane is the gas you put in your car. It's a liquid. Okay? So as these guys get heavier, as they get more and more atoms, you get this particular force, London dispersion forces, becomes stronger. It's holding it together better, making it harder to boil. And that's why you get liquids. It's why the question I asked you about which of these two guys is going to have, you remember the question I asked you? I had a guy like this with two OHs on him. Then I had another guy that also had two OHs on him, but it had way more carbons. You know, it had more carbons. It was a longer chain and had a whole bunch more carbons. I asked you about solubility with those guys, but the boiling point question was pretty simple. If I've got more carbons but the same number of OHs, I'm going to have a higher boiling point for that guy, right? Because the boiling point, the OH, allows me to have, that's going to make a higher boiling point. Alcohols have a higher boiling point just because they have hydrogen bonds that can form between neighboring, in this case, butanol molecules. Okay. So, what are London dispersion forces? I told you they're important in organic. Well, basically, everybody displays this. Everybody, even the guys that have hydrogen bonding are going to display this. However, they're not really important for that. They're important if you have nothing else. They're very important. And it's the attractive force. This is the weird part. I did not explain this well in Chem 1, so I kind of want to do a little bit better job here. Between temporary dipoles. What the heck does that mean, a temporary dipole? Well, think about it. If I've got a perfectly non-polar compound like hydrogen, okay, here's hydrogen, right? And neither guy is pulling harder. So there should be no greater positive charge here or negative charge. It should not exist. They should be pulling exactly equally, like a tug of war. The electrons should be spending perfect amount of time around it. But of course, we know that doesn't happen. Electrons are weird guys. Remember about electrons? They're all over the place. And we don't know where they are at any given time. And they're moving crazy ways around. There's a general shape to them, you know, but they could be at any given time. It may turn out that in that molecule, there's a little bit, the electron's spending a little bit more time over here. Will give you a very slight negative charge on that guy. Guess what that does? If there's a neighboring guy, it will, that little negative is going to attract a little bit, or repel, I should say, electrons from this side and make this side slightly positive and this side slightly negative. So this temporary dipole that just happens by chance induces another dipole, and it's a very weak bond. So if I only have one or two electrons in a very small molecule, it's not held together very well. Like helium, for example. Helium, boiling point and melting points are going to be incredibly low. But look as we go down the periodic table. Look at fluorine, chlorine, bromine, and iodine. Every one of those guys, fluorine, chlorine, bromine, and iodine, every one of those guys is a non-polar bond. Because there's just F to F, Cl to Cl, right? But look what happens. Iodine's got 53 protons and electrons. Down here, he's a solid at room temperature, whereas fluorine is a gas. And bromine is a liquid. It goes right through all the phases. Why? More electrons, greater chance of this happening, and a slightly stronger charge. And that's what the London dispersion force is telling you. The bigger the atoms, the bigger the molecules are going to have a larger London dispersion force because of the greater induced dipole moment. And these are all, by the way, another terminology thing. I call it temporary dipoles. Some people call it momentary dipoles. These should not confuse you, hopefully, okay? Now that you understand it. I never really explained it that well in Chem 1. So again, guys, by random chance, electrons will end up being more on one side than on the other, and that will induce a dipole on the other side, and that's how you basically carry this thing along. So those are the three ways things are held together. All right? The three major intermolecular forces. Remember, I say held together, I'm not talking about an intramolecular bond, an intermolecular bond. All right, I don't need that one. Then there's metallic bonding. Last of the bonding before we get to the problems. I know there's a lot of stuff to cover, but you got to remember this is AP. This is all review. If you were to look back at your notes, you'd find every one of these things done much. I probably spent, if you were to take everything I just covered right now and I'm about to cover, it would be the equivalent of about 2 weeks worth of material. Okay? Easily, because taken out of 3 different chapters. The metallic bond, another classic thing you have to kind of talk about when we're doing, for example, we're going to do specific heats. I just did that little thing yesterday. Right? The black plate that felt cold but wasn't. It was the same temperature as the guy that didn't feel cold. He melted. Why did he melt that ice so easily? The cold, supposedly cold one. Because he was conducting heat from the room into that ice much faster because he was a metal. Metals are great at that. Remember what a metallic bond does. It's just a whole bunch of the same type of atoms that have such a weak attraction for their electrons, they basically just give them up. All right, and they're all floating around like a glue, a sea of electrons. Remember the video and animations I've showed you on that. I only have this one up here right now. Because you have this free-flowing sea of electrons holding all these guys together, if I put a charge to it, the electrons are going to be repelled from one side, attracted to the other side. They're going to carry a current. They're also going to carry heat that way. They're also going to be by the way, all the stuff I just explained. They're also going to be shiny because the light waves will energize those electrons and they'll reflect that energy. They'll conduct and they'll be malleable. I want to talk about that one too. They'll be malleable. Remember this? If I hammer, remember this in the video? If I hammer this guy, normally, if you've got an ionic compound, you like a crystal of salt, and you hammer him, what's going to happen? If I knock these guys down, what's going to happen? This negative is going to come in contact with that negative. Like charges repel. It's going to break apart. That's why ionic bonds are very brittle. Metals are malleable. I can bend them. I could draw them into a wire, ductile, okay? Because if I bang and knock these guys out of shape, the electrons can flow into the gaps. That's the whole point of the metallic bond. All of this stuff that I'm saying, I'm hoping from looking at your faces, sometimes when you're not looking down at your whatever, I'm hoping is you're striking chord. Oh yeah, I remember watching that, I remember doing that. Because I have all the notes again now, and you're going to be asked questions in the homework tonight on some of this stuff. But the thing you're going to have problems on is the stuff I'm going to cover now. Okay, you want to have math problems on. When we're talking about thermodynamics, we could also do calculations for phase changes. Now, these are relatively basic calculations compared to what we're going to do to calculate the energy changes for compounds and reactions. But let's remind you of what we did here. Remember this? Remember this graph? Okay, should look familiar to you. We did it towards the end of last year, actually. Okay, and it is simply a graph of the solid, liquid, and vapor. You should all be on the same page that I'm on. All right, this is also in your paper, I believe, so you should be turned to that page. There you go. There you go. It's not on that one?
Yeah.
Oh, okay. I thought you had the wrong page. Okay. All right. So the solid, the liquid, and the vapor. And by the way, these are by no means to scale. A gas would be much further apart than that compared to a liquid. All right. And what happens here? You notice some weird things about this graph. We notice that, first of all, there's these flat lines. Okay? There's no change in temperature at the melting point and at the boiling point. That's what those are. This is the melting point. This is the boiling point. Because this is the solid, liquid, and vapor phase. Why would there be no change in temperature? Well, Turns out that all the energy you'd be putting in at that point will be going into changing the phase of the substance. So you won't see a temperature change. My grandmother used to say, let the water boil for her tea for 10 minutes because I wanted to get hotter. She didn't get any hotter, did it? However, I used as an example last year why popcorn steam does burn you worse. Why? When you open up a bag of popcorn, all the liquid that was in that kernel turns to steam. Once it all turns to steam, I can raise the temperature. So you're being hit by vapor, water vapor that was hotter than just 100 degrees. Because if I put my hand over boiling water, spaghetti, in a stove, it doesn't burn like that. But you put it over popcorn, it does. All right. There's another reason also that it burns you more. What does that water do when it hits your hand? It condenses into a liquid, doesn't it? What does it give off at that time? All that energy you put into it, the heat of vaporization. That's a lot of energy. So let's look at what would happen, again, using the words we learned yesterday, endo versus exothermic. Going this way, if I'm melting something, or if I'm boiling something, would I call that an endo or an exothermic process? What do you think? Endo. I'm adding energy. Everybody agree? I'm putting energy in it to get it to do that. Everybody gets this right. It's amazing. And if I do this, if I go that way, all right, well, I kind of want to use blue, but okay. All right, if I'm cooling something down and I go from a vapor to a liquid to a solid, I think most people don't realize this. This is one they get wrong. That's exothermic. Here's what I'm saying. Here's why this sounds weird. I'm telling you that when you put your water in the freezer and it turns into ice, that's an exothermic reaction. It's actually an exothermic process, not really a chemical reaction. It's giving off heat. So that's not possible because ice feels cold. The ice feels cold, but it gave off heat to get that way. Do you remember the demo I did? I had a large test tube. I dropped a seed crystal into melted stuff, and it all froze at once. Remember that? Okay. When I passed that around, you were shocked to see that frozen thing felt what? Hot. Because when things freeze, they actually give off energy. So you should be able to determine whether you're absorbing or releasing energy. And now, of course, the last thing you should be able to determine is the actual calculations. I can do a separate calculation at each of those stages. Okay, I already explained both of those things. All right, phase change calculations. Okay, heat of fusion or heat of vaporization. They occur at these points. Basically the points where you're melting and freezing or boiling something. Okay. And you have to be given these numbers. I won't know, even on the AP exam, they're going to give you those kind of numbers. And it won't always be these particular numbers. That happens to be for water. That's all we use in Chem 1. Some of your homework tonight, I think it gives you a list of things. You'll have to figure out which guy it's talking about in that question. All right, here's a good question. Let's do this one together. If you got a question like this on the test or in the homework tonight or whatever, in the AP exam, could you do this now that we've refreshed your memory on it? Should be pretty easy, shouldn't it? Read the question. A sauna, 122 grams of water is boiling, turning to steam. How many kilojoules of energy are required to do that? What do you think? What will I do? Can you look at that without me explaining any more than what I have? It's pretty easy. Just looking at the units is pretty easy. What do you think I should do here, Des? 122 grams by which of these two? The guy, vaporization, V for vaporization, 2260 joules it takes per gram to boil it, to vaporize it. But hold on, don't hit equals at that point. Grams will cancel, but what does it want for my answer in? It wants it in kilojoules. So I'll do one more conversion here. What can I go on the bottom here? Joules on the bottom. No, I'm talking about units. Joules. Always fill the units in first. Joules on the bottom, top. Kilojoules. Which is bigger, a kilojoule or a joule? Kilojoule is bigger, obviously. Kilometer versus a meter stick, right? 1,000. Do the math for all that. What do you get? And keep significant figures. What do you get? Well, give me the actual number. You have to get your calculators out. Give me the actual number on your calculator. Do the math for that. I want to show you about significant figures, too, at this point. What'd you get? 275.72. Okay, so that's the number you get on your calculator. 275.72. You don't have to do it right now. Just let's assume that's right. Anyone else get that? Is that right? Okay. Now, if I had to round that to two significant figures, what would that be? This 5 would round up that 7, right, to an 8. What will I write down? I'm sorry, the 7 would round up that 5 to it. That's 2 significant figures only? Okay, so this 7 will round up that 5, so 276. Is that right? Yeah, 276 would be the correct. I was saying 2 significant figures, but it's actually 3. This guy's got 3. So everybody agree it's 276 kilojoules? Is that right? Okay. I'm assuming that's the right number that you gave me when you did it. So either way, that's how you do it. All right, what's next? Look at this guy. I could ask it in moles. That shouldn't confuse anybody. Look, I know there's a lot of stuff you got to know from Chem 1, but converting moles to grams to atoms should never be a problem at this point. We did it so much in Chem 1. And we actually refreshed our memory again of it in the fermentation lab, that you have to just naturally be able to do this. So I write down my given information at 2.00 moles of sodium. Now let's just say, I'll play devil's advocate. I'm confused. It's been a long time since chemistry. I don't remember what to do. All right, you're confused. What units, by the most basic knowledge, have to go on the bottom? Yeah. So you're a little confused. You think, okay, I know I got to put moles in the bottom. Now I ask myself, okay, I want to know how much heat's released, and I have to look up here. Here's my heat of fusion is 130 joules per gram. Grams. I got to get it to grams somehow, right? So can I go from moles to grams? Sure. Moles to grams. 1 mole contains 22.990 for sodium. And now I'd be in grams. But the question isn't over yet. That's in grams. What do I have to do now? Times by 113 joules per gram. Then grams will cancel. And what do I get for that answer? What do you think? Maggie, what did you get? No, without it. What did you get without significant figures? 5,195. Okay. Okay, well, that's enough because that's too many already. So I got to round out the 3 significant figures. This 5 will round that 9 up. This is kind of a weird one. I love when people do this. I've got to round that 5 up to a 9. There will be people who will say this is the answer. Do you see why they'd say that? Is that the answer? You don't change the decimal place. You're just rounding. All right? And I'm still not correct. What's wrong with that? There's only 2 significant figures. How do I show that that 0 is still significant? I put a bar over. You're like a drunk. You stop at the bar. And you're going from the right. Remember? Okay. Good. All right. Fun times. Now, that is only what's happening at these points right here. There. Okay? It's only how you do the calculations at these points. Melting and boiling points. Okay? What you just learned yesterday, and this is where it really got to me in the other class today, because I realized, what am I going to have to use? What formula am I going to have to use to be able to do calculations of energy changes here? Well, here I've got temperature changes, don't I? Did we get an equation yesterday we could use for that? Yeah. What was that equation? Yeah, mc delta T. Okay, so that's what we got to use for those. So that's what I'm going to show you how to do now for temperature change. Here's your whole, I'm not rewriting it. It's already on your paper. We got it yesterday anyway. Okay? That's all the information. Q equals mc delta T. Mass, temperature change, TF minus TI, and the specific heat. Okay? And you have to be given different specific heats. Maybe that's something kind of important. Why are there 3 specific heats for water? Well, it actually is harder to heat up water or easier depending on what phase it's in, solid, liquid, or gas. So you got to look at the right one to use. All right, so let's try an example problem. I want you to turn your paper over. It's the last one we're going to do today. And we're going to do an example problem. That last paper has a blank side to it. All right, so copy this question down, and I'll show you how you would do it. Is that question on your paper? Yep. Oh, I didn't realize that. Really? Oh, I know why. Oh, yeah. We're skipping these. Why do I not need to do these? These are from, I accidentally put this extra slide in here. This is from Chem 1. We did ones like this just yesterday, right? How hard is that? Q equals MC delta T, right? How hard is that? Same thing. There's no reason. These are from Chem 1. Now we're going to skip to do this harder problem. What happens when I ask all of these guys together? Take a look. If I ask you to do this problem, don't write it down yet. Just look at it for a second. And then we'll copy it on the back of our paper in a minute. But not yet. First, just look. How many steps will this problem take for me to do? Not 3. Not 4.
5.
Not 2.
5.
5. 5 separate problems. How come? Let's take a look. Again, do not copy. Just wait. I'll give you time to copy. Matter of fact, I'm going to shut the video off pretty soon because this problem takes too long to do. We're going to do it in class, just barely get the answer in, but I don't want to have to just let it running for no reason. All right, watch. I'm starting down here. Assuming this is water, this is the melting point of 0 degrees. This is the boiling point of 100 degrees. I'm starting at minus 38, and I'm going to 125. Everybody agree? I'll have to do this calculation to go from here to here because there's a temperature change, right, in a mass that's being heated up that much. I'll then have to calculate how much energy it takes to melt that much ice. I'll then have to calculate, and I will use what to do that, by the way? I will use this equation, the heat of fusion times the mass, like I did in those first two problems a minute ago. Then I'll have to use this equation to go from 0 to 100, and then I'll have to use the heat of fusion equation to do that calculation, and finally the boiling. Once I've boiled it all, I have to heat it up to 125. So I have 5 different things, and what will I do with all of them at the end? Add them all up. Okay? You guys start on that. Copy this question on the back of your paper and show me them like you would show them here. I want you to draw yourself a chart just like this chart here. You don't need to fill all that in here. When you draw that chart, you just have to have. Oops. You just have to have. You don't need that. You don't even need these. Just draw it. I'll know what that means. I mean, you don't have to rewrite those. Draw that chart, labeling the minus 38 and the 125. Those were the two numbers, I think. Okay, I'll give it. All right, so we're good with that? All right. At the end, I will. Yeah. Oh, the question is gone already? Sorry. There we go. Now, which one do you need?
The last one.
Anybody else have that one?
No, wait. The other one.
Oh, that's the last one I have. That's the out of order. All right, try working those out and see how you do.